Hey, Year 12. Okay, so we're continuing with our exam review that we started yesterday. So I'm going to finish off with paper 2, and then I'm going to head on over to paper 3 over the next couple of days during our lessons online. Okay, so I'm just going to jump straight back into it, try and get it done within the hour. That's the hope, anyway. Right, okie-dokie. Okay, so question 23. This question is about halogenoalkanes. Bromoalkanes react with aqueous. It's nice to pick up conditions here, folks. Yeah, aqueous. And we've got potassium hydroxide as our reagent. So our reagent is KOH. That is the reagent. Remember, the reagent is not the same as the reactive species. The reactive species is the OH minus that we're going to be using in our mechanism. Don't like that being over there. Put the charge on the atom that it belongs to. Oh, hey, Kayun. Hey, Ivan. Hey, Donna. Thanks for coming along. It's really great to see you guys. Thanks for coming. Okay, so the condition, of course, being potassium hydroxide. I'll underline that instead of circling it. This condition suggests nucleophilic substitution, suggests NS. We realize that the OH minus ion can do two roles in organic chemistry. It can either act as a nucleophile, which is warm, aqueous, dilute conditions. Mr. Duncan, you're not sharing. Oh no! Thanks for that. You're right. Have you just been looking at my forehead? Oh, you're right. I didn't. Thank you so much. Good thing I've got the other screen up. Otherwise, I just would have done the whole chat. That would have been hilarious. Do you know what I'm going to be investing some? I'm going to buy myself a good webcam, a separate one, so that I can write and you can still see me. So I can have that because I'm waving my arms around all over the place as I normally do. And it would be nice for me to be able to do both of these things with you. Okay, so going back to the question. So question 23, this is where you guys are all up to. And I was just talking about how the OH minus ion, that reactive species, can do two roles. We know that the OH minus can do nucleophilic substitution, which is in warm, aqueous, I'll just put AQ, dilute, dilute conditions. Yeah, but we also have elimination as well, and we learned that one with a chelimination. Yeah, I'll do that underneath it. Chelimination, which is concentrated hot ethanolic conditions. So that one then, ethanolic. There you go, WOD and chi. But chelimination is the way that I tend to remember that. And then you realize one of the great things about chelimination works so well because it just rolls off the tongue so nicely. And if you actually just look, you can get, so you recognize that in chelimination, you get the letters which then give you your conditions. But then if you want to do nuke sub, you just go for the opposite. What's the opposite of concentrated? It's dilute. Dilute is the opposite of concentrated. What's the opposite of hot? Right, you're not allowed to say cold. Now, there is a reason for that. Yeah, we know that we can't do organic chemistry during cold conditions. There are some reactions, actually, by the way, for A2, where you do them cold. You actually do them at very specific temperatures, around 5 degrees Celsius. But most of the time, you need to warm them because you've got to break covalent bonds, and that requires activation energy. And covalent bonds are strong, so we need them to be at least warm. And then, of course, the opposite of aqueous literally means in water, and ethanolic, they're opposites, because if you go out on a night out, you're either drinking water or you're drinking alcohol. So that's the way I tend to do that one. So, okay, draw the mechanism for the reaction between 1-bromopropane and aqueous potassium hydroxide, include Kelly-Iris and all relevant lone pairs and dipoles. Okay, so 1-bromopropane, it's nice and easy. Can I just point out, by the way, this is a very simplistic, this is a very, very AS level question. Yeah, this is CD level. So first thing you do is find your delta, and the only delta there is your carbon-bromine bond. And then we're going to have our nucleophile of OH minus. Notice how I circle the charge because it's a full charge. Yeah, students often say, can I The internet is an amazing resource, and it's got some great chemistry on it, but it also has some terribly bad habits on it and bad chemistry. You know, in organic chemistry, you should always put the charge on the person it belongs to, and if it's a full charge, you should circle it. This is to prevent it looking like an electron. Now, the delta tells you where it's going to attack. So we're now going to do a nice solid curly arrow straight from the middle to the C. Notice where I'm starting. Yeah, I'm not starting here. I'm not starting here. I'm not starting here. Yeah, I'm starting dead in the middle of the lone pair of electrons. Yeah, there you go. There's my first curly arrow. Now, that arrow literally means I'm making a bond. That carbon cannot have 5 bonds. So we're then going to have a second curly arrow of that bond breaking. Notice that bond breaking, again, the curly arrow is very specific. Yeah, I am starting on that bond. Yeah, I am literally starting at it. Yeah, touching it. I'm not floating above it or below it. Yeah, I'm actually starting, touching it, and then I'm just going across, making sure that they can still see my delta. So there you go. Make sure the arrows also look like they've got complete heads. So there's my 4 marks. Do they want anything else? No, that's it. Nuke sub. I'm also going to draw the product. They're probably going to ask me to do that anyway. So I'm going to draw the product anyway. Yep, so we've now formed propan 1-ol. Yeah, you've got to have that 1. But the marks are all in the mechanism. You don't actually need the product. The products tend to be asked for in later questions. Then I draw the product. Hi, Ria. Lovely to see you. Do you know what? I was really disappointed, Ria, when you weren't here at the beginning, because you know you were so excited about seeing my lesson. By the way, hi, Tanzi. Sorry I missed you before. State the type and mechanism of this reaction. Isn't that interesting? Type and mechanism. Well, that is a nucleophilic substitution. Nucleophilic substitution. Now, isn't that interesting? I do actually want to check the mark scheme there, because the type and mechanism, the type of reaction is a substitution. Yeah, the mechanism is nucleophilic substitution. I think that's fascinating, that. They're writing that down just to confuse you. 2 marks, that's 2 marks, that, folks. 2 marks for each of those works. I'm sorry. Oh, Ria, you don't need to be sorry. Don't be silly. I do want to check that mark scheme, though, immediately. I don't even know where I'd go about finding it, to be fair. Let's have a quick look. I don't have a PDF reader, apparently. It will be nucleophilic sub. There's no other option it could be, really. See if we can track it down. I'm on question 23. That's where I am. Import, no thank you. I'm on question number 23. Don't ask again. Right, there we go. Nucleophilic, 1 mark. Reject homolytic, and substitution is the second one. There you go. Nice that. Now, I'd like to think that you guys, you know, nothing ever ends in chemistry. There's always an extra level to this. There is an additional level on top of that, and you'll see that in the mark scheme. I shouldn't really point it out, to be fair. Ignore reference to SN1 and SN2. That's because lots of teachers like myself would really like to actually just teach it properly from the beginning rather than adding in the A2 bit. But I'll cover that in one of our A2 lessons in the next coming weeks. Okay, a nice reacting mass question. By the way, straight away, the type of reaction, I'd like to think that every one of you would be able to get this immediately. Notice in out. If you've got in out, this is elimination. We're done. Straight away, can't be anything else. Yeah, in out. Yeah, it's out because it's on the outward side, the product side of that reaction. So in out is elimination. And they're going to want us to do a mechanism? No, it's a calculation. 0.5 grams, so I'm going to write that underneath there, of 1 bromopropane reacts with potassium hydroxide in ethanol. There's the elimination. There's elimination. The volume of propene formed at room temperature. So the propene was 18 centimeters cubed. Calculate the percentage yield of the propene. That's actually really nice, actually. So the first thing you're going to have to do, just to point out, by the way, you guys need to be aware that these papers are not testing you properly. You are not covering PV equals nRT. Yeah, PV equals nRT is new for your specification, but if you do the booklets that I created you'll be doing them. Please make sure you are. So the first thing is chemists don't work in grams, we need to get to moles. So the number of moles is grams over rams. We know this. Right, so we now need to work out the MR of 1 bromopropane, so 12 plus 3 plus 12 plus 2 plus 12 plus 2 plus 80. 123, I believe. 0.0. I would have lost a mark because at A level, everything comes to 1 decimal place. We know this. Just going to quickly check that. 12 times 3 plus 7 plus 80. There you go, 123. I like it. So we now get 0.50 divided by 123.0, and I get a number of moles of 4.07 times 10 to the minus 3. If you put 0.6, then you're going to lose it. And that's moles of 1 bromopropane. Next, the ratio, of course, which this is one of the most lost marks in all of chemistry. The ratio is 1 to 1, if anybody's wondering why. The reason being is because there is an invisible 1 here and an invisible 1 there. So the moles is the same. We're okay with that. So we can put 4.07 times 10 to the minus 3 moles of propene. But then the thing is, it's told us 18 centimeters. Well, they want us to work out the percentage yield. So if that's the moles that we should have got, well, we can work this out as centimeters cubed, can't we? Number of moles is V over 24,000 because I'm in centimeters cubed. Yeah. So if I go, I've got my moles, just bring that over. So if I rearrange that, it becomes 24,000 multiplied by 4.07 times 10 to the minus 3. Now you notice, by the way, not that you do, but I've got that number, the actual number on the calculator, which is 4.06504065 times 10 to the minus 3. So I've got the real number on my calculator. I'm just going to multiply that now by 24,000. And I should have got 97.6 centimeters cubed. Again, I'm keeping the real one. It says do not write in this area. Yeah, I'm just going to move that a little bit. So I'm just going to do equals 97.6 centimeters cubed. I'm keeping the real number on my calculator though. So now I want the percentage yield. Percentage yield is actual over predicted, actual over theoretical times 100, theoretical times 100. So I'm going to go actual is 18 over answer times 100, and I get 18 points. So I get 18.45%, and I'm done. That's the yield. Terrible yield, by the way. Horrendous. Next, an experiment was carried out to compare the rates of reaction of 1 chloro, 1 bromo, 1 iodo react separately with water in the presence of silver nitrate. Identify the halogen with the fastest rate of reaction. So the fastest rate is 1 iodo. So fastest rate is 1 iodo. 1 iodopropane. And there might be people in the room going, I don't understand why. Yeah, and justify your answer. The reason being is because the iodine carbon bond is the weakest compared to chlorine carbon and bromine carbon bond. So if it's the weakest, we realize it's all about bond enthalpy, not bond polarity. The one that's the most polar is the chlorine carbon bond, but the one that reacts fastest is the iodo because the bond's longer and weaker. Okay, CFCs have been used as aerosol propellants. Right, just to explain to you what that means, a propellant is if you have a deodorant can, yeah, you have your little deodorant can. There we go. So you got your deodorant can. And inside the deodorant can, you shake it and it feels like you've got a liquid. Now, the reason for that is because you have a gas which has a boiling point very close to room temperature, and they've compressed it. So this gas, the gas is under pressure. Under pressure. It is under pressure, so becomes a liquid. Becomes a liquid. And then when you press the button down, you release the pressure and it boils. Yeah. And CFCs have got boiling points very close to room temperature. That's why they were ideal. By the way, they're terrible for the environment, terrible for the ozone layer. Draw the displayed formula of the CFC. Okay. So first thing is it's an ethane. Next, I need 1,2,2-trifluoro. 1,2,2-trifluoro. 1,1,2. There we go. Now that's interesting, isn't it? They have counted, notice that they have counted from this carbon. That's because all of these atoms that are attached are all halogens. They have exactly the same ranking. What that means is you just go alphabetically. So you want to choose the Cl to be first. But there you go. Next, chlorotrifluoromethane breaks down in the ozone layer to form free radicals. Suggest a reason why fluorine free radicals are not produced. The carbon-fluorine bond is exceptionally strong. Yeah, carbon-fluorine bond, very strong, so not broken by UV light. UV light doesn't have enough energy to do so. Right, chlorine free radicals, write the 2 propagation steps in the chain reaction. Right, so the Cl dot, I'm actually going to give you the whole thing. The initiation of this actual process, it's not required for this question, but I'm doing it anyway. You put in CFC, let's say we actually use the one that they chose. Yeah, trichlorofluoromethane, CCl3F. They add that, you have UV light, and what you end up with is Cl2F, and the dot is on the C, and you have a Cl dot. Now that Cl dot is now this is where your question here begins. The Cl dot now collides with an O3, and it rips off an O, and it becomes ClO dot on the O. Now I know that's confusing, folks. And I've explained this to you in lesson. I walked you through the dismantling of the ozone molecule and how the fact that there's always this leftover electron on that oxygen. That then goes back in. This is a chlorate 1 free radical, and that hits another ozone molecule, and that makes Cl dot plus 2 O2s. And what you realize is that that's for the 2 propagation steps. Curly arrows are not required, not a real mechanism, just a series of equations. So there's the 2 reactions. You can put them together if you like. It's nice to show you that the Cl is a catalyst because it goes in here and it is regenerated at the end, so not used up. It is providing a completely different pathway because the overall reaction, of course, is just 2 O3s going to 3 O2s. So that's the original route, and this is a completely separate route, and the Cl dot is not being used up. Nice to kind of talk you through. This is the overall, by the way. This is the overall equation. Next, butane is now used as a propellant in some aerosols, as it does not form free radicals in the ozone layer. Give one disadvantage: butane's flammable. Yeah, butane is flammable. Yeah, that's how you get your flamethrower deodorant can whenever you go camping. That's why, because they use butane. Next, section C. Cool, we're heading towards the end of the paper now, really, folks. Okay, this looks like it's going to be complicated. Explain in terms of the oxidation. By the way, I'm jumping straight into the question rather than reading all the waffle. Don't see an awful lot of point in it. Explain in terms of the oxidation numbers of nitrogen and chlorine why the reaction between ammonia is called a redox. Okay, so the oxidation state of nitrogen, let's zoom right in here, folks, as far as I can get. The oxidation of nitrogen here is -3. Hydrogen, of course, is +1. Sodium, of course, is always +1, but the chlorine is in a very funny one. That's a +1 and a -2. So chlorine is also in a +1. That's special. I'm assuming. Oxygen, of course, is in a -2 as normal. Nitrogen here is in a 0, right? So there is our first reaction, our first part of the redox. Sorry, how does increasing pressure increase the boiling point of something? Huh, great question, Kayan. Ooh, that's exciting. Okay, I'll explain. So let's say we take water, yeah, as a liquid, and we have water becoming a gas. Now, what you guys don't often get, the level of detail here is rather difficult, and where to put it in is quite complicated when it comes to being a chemistry teacher. But we all know that that change there, everyone, of course, can name it, that's boiling. But we also know that the process is a physical change. This is a physical change. It is a physical change. That's that's Key Stage 3, Year 7. And it is also reversible. Reversible. That's also Year 7. What that means is the arrow is wrong. The arrow is wrong. Right.
Yes.
So,
yes. Thank you.
So Kayan, now that we recognize that it's reversible, we can now apply COFs to this. Yeah. Remember, we can treat this like an equilibrium. So let's say we raise the pressure. We know, by the way, that this usually takes place at 100 degrees Celsius. Yeah. Well, what we then realize is we are going to increase, question is increase pressure. So, okay, run the process of COFs. Knowledge, right? Look at the particles on each side. And the only one that's important is that one, because pressure only affects gases. Only gases. So what that means is, Ange, hey sir, I haven't done the 2016 May paper, but I did the 2015 May. Is it okay to do? I have to do them. Yes, I do want you to do them, Ange. Come on, get on with it. So Kayan, back to yours. The knowledge is that you have one mole of gas on right side. This is the right, this is the left. On right, 0 on the left. 0 on left. It's a liquid, therefore gases don't have any effect on it. Yeah? Sorry, pressure has no effect on it. So now oppose the change. If we increase pressure, the equilibrium reduces pressure. How does it reduce pressure? Yeah? Reduces, I'll zoom out a little bit, reduces pressure. How does it do this? What does it favor? Favor the side with less gas. Favor side with less gas. Side with less gas. Shift right to left. Shift right to left. The gas becomes a liquid. Therefore, you're just going to turn. So in order then to push the equilibrium back towards the gas side, we've got to raise the temperature to compensate for the high pressure. The pressure will push it this way. High pressure, high P pushes it this way. Yeah? Which means the gas becomes a liquid. If I wanted then to push it back to being a gas, I'm going to have to raise the temperature to compensate. Hence the boiling point increases. What a lovely question, Kayan. I'm so glad you asked it. That's hard, but it's not difficult. It's just equilibrium. And the recognition that pressure only affects gases, and in a state change, there's only gases on one side. Really great question. Thank you for asking it. Does that explain everything, by the way? So we can now say, first bit we've just identified here, nitrogen starts in a -3 oxidation state, and ends in a 0 oxidation state. Let's write the half equation. Oh, that makes sense. Thank you. And this happens with all liquid gas state changes. Yes, it does, Gayan. Absolutely. Absolutely it does. Yeah. Right, let's write the equation for that. I'm going from ammonia and I'm forming nitrogen. Right, year 12s, I'd like you to pause the video and can you balance my half equation, please? Pause the video. Right, we're going to be running for a half equation. We are going to be running my process of kissing a half equation. Mwah, or moe. I quite like weighing equations because, you know, balancing them with a weighing scale, so I'll stop. So we've got metal. So in this case, the metal is actually anyone who isn't oxygen and hydrogen. So this is nitrogen in this case. So I've got 1 nitrogen and 2 nitrogens. Got to do that first. Right. So nitrogen, done. Next one, water for oxygen. Yeah, water for oxygen. Don't have any oxygen. Winner. Next one, acid for hydrogen. I have 6, so I need 6 H pluses over here. Done. Next one, electrons for charge. Yeah, electrons, and we get E minus. Right, we've got on this side total charge of 0, on this side total charge of +6, so I'm going to add 6 electrons to that side, and I'm done. Winner! So, nitrogen starts in a minus 3 oxidation state and ends in a 0, so loses electrons. Loses electrons, brackets, right, oxidation is loss, therefore oxidation. I like it. Okay, next. Now we go to sodium is still +1, it's always +1. Chlorine has gone to a -1. We've just identified our second one. So we're going from sodium chlorate to sodium chloride. So we've got, just having a drink, sorry. So we're going to state in words, chlorine starts in a +1 oxidation state, and ends in a -1 oxidation state. Let's do the equation. Right, so I'm going from sodium chlorate to sodium chloride. Isn't that nice? Right, guys, pause the video, moe me. Yeah, so we've got metal, so this is sodium, already done. Water for oxygen. I've got 1 oxygen, so I need to add H2O to that side. Next, I need acid for hydrogens. 2 hydrogens have just appeared over there, so put 2 H pluses over here. Next, electrons for charge. Overall charge is +2. Overall charge is 0. Add 2 electrons to that side, and I'm done. There we go. And it's gaining 2 electrons. Brackets. Gaining electrons. -1. Gaining electrons. Gaining electrons is reduction. Therefore, I've written everything all over the place. Brackets. Reduction. I like it. Winner. I think that's quite a nice question, actually. Really enjoyed that. Cool. Next. Okay. We're doing really well. I think we're nearly at the end. Nope. Total lie. Got miles to go yet. Next. Calculate the minimum volume of 0.2 moles per decoculated sodium chloride solution needed to react with. Okay. Right. I hate this. This doesn't teach you PV equals nRT, and you need it. I'm sorry, guys. You won't get V over 24 anymore. You won't get it. But we're going to have to use it here, which is really annoying. So I've been given 120 centimeters cubed. Number of moles is V over 24. So we've got, that's going to be over 24,000 because I'm in centimeters cubed. Yeah. So that's going to give me moles of ammonia. 120 divided by 24,000 gives me 5 times 10 to the -3 moles of ammonia. Okay, next. It says calculate the minimum volume of sodium chlorate. Right, it's asking for some of this. So the ratio between these two, so the ratio, which again, lost mark so heavily, is a 3:2 when we're moving in that direction. So we need to use the ratio, and we're going to say divide by 2 times by 3. Divide by 2 times by 3, and I get 7.5 times 10 to the minus 3 moles of sodium chlorate. And what was its concentration? It was there. Right, number of moles is C times V over 1,000. It's not complicated. It's the same process you're running every time. Some of them can be hard, but not complicated. Reorganize it. Number of moles times 1,000. All over C gives me V. Right, times that by 1,000. Divide it by a concentration of 0.2. And I get 37. So I'm just going to write that out. 7.5 times 10 to the minus 3 times 1,000, which just makes the 10 to the minus 3 vanish, by the way. Divided by the concentration of 0.2, and I get 37.5 centimeters cubed, and I'm done. Next, ammonia formed in the Haber process. Explain the effect, if any, on the position of equilibrium when the temperature is increased at constant pressure. Right, so we're running COFs as normal for equilibrium. We get used to this process. So knowledge. For temperature, the knowledge is all about the reaction in terms of enthalpy change. So knowledge. The forward reaction is exothermic. Forward reaction is exothermic because it's minus. Nice and easy. Next, oppose. If we increase the temperature, temp, the equilibrium will reduce temperature, will reduce temp. How will it do that? So move favor down. Yeah, how will it do this? It will therefore favor the endothermic reaction. Shifting. So the endo is the backward, so it's going to go that way. So it's going to be shifting from right to left, shift from right, because this is shift from right to left, yield decreases. Done. I like it. Use Maxwell-Boltzmann's distribution to explain why the addition of a catalyst increases the rate of a reaction. Right. So, and now she says use it. So if this there, I shouldn't actually do that, by the way. If I just label this one here as this is the activation energy, and I could actually put brackets original, and then I can also go, okay, that one there is activation energy with catalyst. And then what you do is you kind of do this, and you go, the number of particles. It's asking you to explain how a catalyst is also functioning here, folks. I hope you kind of got that. Yeah, so this is kick-ass. Hang on a minute. It's not really, though, is it? It's catalyst. It's kind of special. Knowledge. Catalyst provides an alternative route of reaction with a lower, underline that, with a lower activation energy, more particles, as shown in diagram. More particles have activation energy, EA. So more successful collisions, rate increase. I like it. I bet 2 of the marks are just for the graph. Complete the reaction profile of the catalyst reaction for the formation of ammonia. Ooh, that's quite clever. Formation of ammonia, the equation states that it's exothermic in the forward direction to make ammonia. Right, so it's exothermic, so your products are going to be lower. Products. And it says, complete the reaction profile of the catalyzed reaction for the formation of ammonia. Label the activation energy and enthalpy change. Oh, it's really interesting. With a catalyst, there's no comparison. They want a shelf with a catalyst. Yeah, and they're showing this there is the intermediates. Intermediates. That's very interesting. Catalyzed route. Activation energy is that bit there. That's the activation energy. There's actually 2 activation energies, but only one of them matters because one's bigger than the other. I want to see a mark for that. That's really interesting. That's 3 marks. Intermediates like catalyst shelf. And it says label the activation energy for the forward reaction. So that there will be activation energy. Act energy. Yeah. Yeah, I'd like to look at a mark scheme. We'll do in a minute. Ammonium chloride reacts with nitrogen trichloride and HCl. Write an equation. Ammonium chloride. So they're testing to see if you know how to do complex ions. Ammonium chloride reacts with chlorine to form nitrogen trichloride and HCl. Balance it. 1 nitrogen, 4 hydrogens. 4 hydrogens, chlorines, lots. So we've got 7. So we've got 1 in that. We just need that to give us 6. I like it. Include state symbols. Oh, that's clever. Ammonium chloride, by the way, is a salt. It's a solid. Yeah, chlorine, of course, is a gas. That's hard. Nitrogen trichloride. Oh, nitrogen triiodide is a solid. Oops, wrong video. I'm going to assume that's a gas, and HCl is definitely a gas. I don't know whether or not nitrogen trichloride would be. It will be a gas. It's a very big, heavy gas, though. That's tricky, that. Not 100% sure. But ammonium chloride is solid because it's ionic. Predict the shape of nitrogen trichloride molecules. So NCl3, it's in group 5, plus 3, adjust for charge, there isn't any, 8, 2, 4, it's tetrahedral, straight away. Instantaneously, that's tetrahedral, but it's not, is it? Ah, there you go. It's pyramidal. So the shape is pyramidal. Yeah, and they're going to ask you to justify it, and you've got to go, right, so we know this trick, which is bonding pair, repulsion is less than bonding pair, lone pair repulsion, which is less than lone pair, repulsion. But we stop here, we stop there, because there aren't 2 lone pairs, there's only 1. So you would say justification, bonding pair, repulsion. And yes, you've got to write it all out. Bonding pair, repulsion. Bonding pair repulsion is less than bonding pair lone pair repulsion. So repel. So angle decreased. So angle decreased, annoyingly. Angle decreased. Kind of want to see a mark scheme for that as well. I'm going to go through the mark scheme entirely in a minute. Okay, explain in terms of intermolecular forces why nitrogen trichloride has a similar boiling point to ethanol. Oh, that's clever. So we're going to say NCl3 has dipole attractions. Has dipole attractions between molecules. Ethanol has hydrogen bonding, but which is has hydrogen bonding, but NCl3 has a larger MR, so has stronger London dispersion, or Van der Waals forces, whichever one you want to use, has stronger London dispersion forces, or Van der Waals, stronger Van der Waals, so making boiling points, BPTs, similar. Again, want to mark it. I think that's the end of the paper. Wow, want to see the mark scheme for that whole last question. That was hard. Let's have a look. Oxidation numbers. Yep, that's all good. Calculation. 37.5 looks good. Equilibrium, shift towards reactant, ammonia formed, right reactions, exothermic, all that jazz. Activation energy labeled and then with a catalyst, and then more molecules have activation energy. Fine. Yeah, there you go. Oh, I missed the enthalpy bit. Was I meant to label the enthalpy change as well? I knew I'd missed something. There you go. I'm not infallible. I knew I would. I just thought it was horrible. It says label the actor and the enthalpy change. Enthalpy changes. There's the enthalpy change. Delta H. Easy miss. Sorry, really quick. The NCl polar, the electronegativity chlorides are similar. Are they? They could well be, Ria. Not really considered it. I just kind of saw nitrogen and figured it would be. You're right. It probably is actually non-polar. No, polar. Fluorine's, remember, the only person you need to know is fluorine, and she's 4. Yeah, and then you move 0.5 away. 3.5, 3, 3.5. It's polar. You're going to argue and say chlorine's not 3.5, it's slightly lower. It's still polar. They still want you to say it. Check the mark scheme. It's going to say polar. Balanced equation. Bam. Pyramidal, love it. 3-dimensional picture. Oh, allow it. I like it. Electron pairs, 4 pairs, 3 bonding, 1 lone. Repulsion separates electrons arranged to minimize repulsion. Electron pair arrangement for maximum separation. Ignore lone pairs repel more than bonding pairs. Oh no! Oh, I lost it. 3 bonding, 1 lone. Oh, well, we definitely would have got that one anyway. Yeah. And then done 3rd mark repulsion. So I need to be saying repulsion, electrons arranged to minimize repulsion. That is something I want to be saying. Definitely, I like that. Or is it polar because of the presence of the lone pair? Yes, absolutely. The lone pair is going to mean it's polar as well, but the bonds are also polar. The whole thing's mental polar. The lone pair especially. Yeah. Yeah. Arrange to minimize repulsion. I'll put that in red. Just remind me to write it next time it comes up. Arrange themselves to minimize repulsion. There we go. Last one. Hang on. There we go. First, nitrogen both have London dispersion forces. Okay. Yeah, that's irritating. Instantaneous dipoles and induced dipoles. Oh, 2nd mark. London dispersion forces. Yeah, okay. Nitrogen has more electrons. Yeah, 3rd, ethanol has hydrogen bonding. Certainly got that one. London dispersion forces, because it has 58 electrons, where ethanol only has 26. Yeah. You can also say that in terms of MR if you want to. So I definitely get 2. I just don't get the other one. Did I write it down? Has dipole between the molecules, ethanol has hydrogen bond, but has higher mass, so strong Van der Waals. Strong London dispersion, so makes boiling points similar. Yeah, I definitely want to say both show them. Yeah. Anyway, I'd say that was a pretty nice paper, to be fair, and well worth going through. I'll try and bring you guys all back now. That one. Hey, guys. Right, I'm going to leave you be for the rest of your Sunday, and I'll see you in school tomorrow. Well, not in school, but I'll see you in here. Guys, have a great rest of your Sunday.